Ready?
Yeah. Alright, so today we're considering the Compton scattering effect. So in order to do so, we're first going to consider the classical case of two pool balls colliding and bouncing off each other. So first of all, on our pool table we have a cue ball, we'll call that M1. And it goes with a velocity, call that U1, that's a vector. And it collides with a pool ball and then it goes off in this direction after collision. Call this, it's still M1. I'll call this V1. Then there's another pool ball going this direction as a result of the collision, so we'll call this M2, and it has a velocity of V2. And the angle between the two pool balls after collision is, call this one theta, and this one phi, with respect to the horizontal plane. So from here we can set up our energy equation to show the energy before and after collision. So first of all we have E1, this equals E2, it's conservation of energy. And so E1 is equal to the energy of the cue ball, it's M1, so it'll be 1/2 M1 U1 squared. And it's a scalar in this case because it's energy, and energy doesn't use vectors, so that's why there's no hat there. So that's going to equal 1/2 M1 V1 squared. And so we have that plus 1/2 M2 V2 squared. And so if we can see from this equation that the initial energy will always be greater, of the cue ball, will always be greater than the cue ball after the collision. So the cue ball after collision always loses energy, according to conservation of energy. So now we have our own measurements for our actual collision that took place. And so for the speed of the cue ball initially, U1, we have that equal to 1.2 meters per second. The cue ball after collision, its speed is 0.58 meters per second. And then we have the mass of the cue ball, M1, that is 0.170 kilograms. And so from now we can compare the two energies of the cue ball before and after collision. And if we do so, we end up with 1/2 times 0.17 times 1.2 squared, which ends up being 0.1224 joules. And this is before collision. So now we do the same thing for after the collision. We have 1/2 0.17 times 0.58 squared, which gives us a significant decrease in kinetic energy. It's 0.02859 joules. And so from here you can see that before and after the collision, there's a huge difference in the kinetic energy of the cue ball, which we'll find is also the case for when a photon scatters off an electron in the Compton scattering effect. All right, good to go.
All right, so this is Compton scattering. So Compton scattering, you have a photon approaching an electron. And when they collide, the electron goes off at some angle, and the photon scatters at another angle. When the photon collides with the electron, it loses some energy. So we can derive the formula for Compton scattering using energy arguments. So let's start with conservation of energy. So energy of the photon plus the energy of the electron is equal to the energy of a photon after the collision plus the energy of the electron after the collision. And we're also going to use conservation of momentum. So we have momentum of the photon is equal to momentum of the photon after the collision plus momentum of the electron after the collision. And we're assuming the electron has no momentum to start with. So we also know the energy of a photon has that formula, h times f, so Planck's constant times its frequency. We know that the electron has an initial energy of its rest energy, so E electron mass times c squared. So then the energy after the collision of the photon, h times f prime is the frequency after the collision. The energy of the electron after the collision, since it has momentum after the collision, we can write it like this. So we have these, we can substitute these into our conservation of energy equation, and it gives this. So we have the energy before plus the energy before of the photon and the electron is the same as the energy of the photon after the collision plus the energy of the electron after the collision. So from there, we can rearrange so that we can get this guy by himself. So after we do some rearranging, P E prime C squared is equal to HF minus HF prime plus all this squared minus so now that we have this, we can call this our equation. Well, this is equation number 1. This can be equation number 2. So now that we have that, so now we can move on to our equation of momentum. We can rearrange for this guy. E prime equals. So we have this. Momentum of the photon after the collision is equal to momentum of the photon minus the momentum of the photon after the collision. So we can also rewrite that this way. So here we're using de Broglie wavelengths. Since h over lambda, we know that lambda f equals c. So f over c is 1 over lambda. So when we rearrange, we can write momentum in this way. So from here, I'm going to say okay, so that's just rearranging the HF minus HF prime. So we can also note that when we square this side, it's the same as the dot product, so we can say, I'll move over here, P prime squared equal to P. Doing dot product here, and we also know that P of the electron after the collision is the same as P of the photon minus P of the photon after collision, so we can write, after a little bit of algebra, P of the photon squared plus P of the photon prime squared so doing this gets rid of all the vectors. We have scalars here, and if we multiply the entire equation by c squared, and also noting that momentum times c is the same as energy because h, c over lambda is energy. So we have P prime squared, e squared. So we can call this one our equation number 3. Yeah, make a little bit of room here. So if we set our equation number 2 and 3 equal to each other because PE squared, C squared, PE squared, C squared. We set them equal, and we have setting them equal to each other gives this. After rearranging this guy and canceling some terms, we end up with 2 squared. So we have this, and dividing by 2 times h times f prime, also times m times c, divided by all that, gives us this. So, noting that, again, lambda f equals c, we can rearrange this to be lambda, so this was lambda prime, lambda, so lambda after collision, lambda before collision, that's the wavelength of the photon. So we have this is our good old Compton scattering equation. Basically saying that after the collision, it has a certain wavelength, and before the collision it had a certain wavelength. The wavelength has a net gain positive, which means that the wavelength gets longer, the frequency, so the energy gets smaller. So there's a net decrease in the energy.